Good morning, Algebra 2 students. Hopefully all is well in the algebra world. Today what I'd like to show you is, in addition to this do now on graphing linear functions, I'd like to show you how you can identify characteristics of functions just by looking at a graph, be it a graph of a linear function or any old type of function. The domain and range, things that we've already learned, are characteristics of functions. So there's two that you already know how to do, but we are going to take a look at a couple more of them today. All right. Just really quickly though, if you want to treat this like a true do now, I would recommend pausing the video, trying to do this problem on your own, see if you can convert this to y equals mx plus b or slope intercept form, and then sketch a graph of it. I'll give you a second to try to pause the video and make that happen now. But by now, I assume that you have paused the video and have tried to come up with your own equation and graph. This should come out to, I'm pretty sure, y equals negative 1/2 x plus 5. So hopefully you got that. If you didn't get that, then let's see what we can do about that. So starting out here, I'm pretty sure everybody at this point would know, as soon as we see distribution, we should make that happen right away. Why leave that ugliness in there for any longer than it needs to be? Let's distribute the 2, giving us 2y here, 2 times y. 2 times 2x plus 4x is equal to 7x, just stays by itself, plus 10, 2 times 5, minus 4x, 2 times negative 2x. Everybody see that? Now we can go forward from here, and I get 2y plus 4x on this side, no like terms to combine, but ooh, there are some like terms to combine over here. I'm going to leave my left side alone for now. My right side, we have 7x, take away 4 of them, leaves us with 3x's left, and then plus 10. All right. Now, if I want to make this look like y equals mx plus b, right? Remember, that's my goal of anything in a mixed form. My goal is to convert it to slope-intercept form, because that would make this nice and easy peasy. How do I do that? Well, I have these x's currently on the left-hand side of the equation. I don't really want them there, so we're going to move them out of the way by subtracting 4x on both sides. Gets me 2y is equal to 3x minus 4x is negative 1x, and then plus 10. And lastly, I don't really care about 2y. I just want 1y by itself. So let's undo that multiplication of 2 times y by dividing everything by 2, leaving me with y equals negative 1/2 x plus 5, just like that, right? Now we have our negative 1/2, which is the slope. That means, remember, slope is rise over run. We're going to go down 1 and down because it's negative, down 1 and to the right 2. This is our y-intercept, right? So I'm going to sketch that graph by going to my coordinate plane down here. I'm going to start at my y-intercept of 0, 5, 1, 2, 3, 4, 5 right there. And I'm going to follow the slope by going down 1 unit and to the right 2 units. And then from the point I just plotted, I'm going to continue to do that, down 1 unit to the right 2, down 1 to the right 2, down 1 to the right 2 until I'm satisfied, down 1 to the right 2. If you wanted to extend it in the other direction, you could certainly go up 1 and to the left 2, because it would just continue that straight line, right? You can see that line forming with all these points that we've plotted. Now we're going to connect them, and we end up with a graph more or less like that. I didn't use a ruler, but that's pretty close. Okay? In addition, just to review the idea of, instead of using this idea of starting at the y-intercept and following the slope to sketch a graph of this, just to review the concept of using x and y-intercepts, that's certainly something that you can do. So you could find the x-intercept, and to do that, you're going to plug in 0 for y. I'll just write it here to remind you. Plug in 0 for y, because any point in which the y-coordinate is 0 will be sitting right on that x-axis. So that would mean 0 is equal to negative 1/2 x plus 5. And we should be able to solve that equation for x to find what our x-intercept is. If I subtract 5 over to the other side, that gives me negative 5 is equal to negative 1/2 x. And how can I get rid of that negative 1/2? Well, of course, I can divide by negative 1/2 because it's negative 1/2 times x, or you could choose to multiply by negative 2. And that will give me my answer of positive 10 is equal to x, because you notice multiplication of negative 2 would undo multiplication of negative 1/2. multiply by the reciprocal to undo a fraction. Certainly you could divide by -1/2, but dividing by -1/2 is the same as multiplying by a reciprocal, because that's how you divide by a fraction. Anyway, I would get my x value to be 10, meaning that my x-intercept would be at 10, 0, which if you notice, that's exactly where it is. And if you do your y-intercept, you would do your y-intercept by plugging in 0 for x, because any point at which the x-coordinate is 0 means we're sitting right on that y-axis. We would get that y, this one's a lot easier, y equals -1/2 times 0 plus 5. Obviously, -1/2 times 0 is 0, so you would just get y equals 5, which is your y-intercept of 0, 5, right here. So what you could do is just draw your two intercepts on the graph, or plot your two intercepts, and then connect them, and you get your nice line. Okay? This is actually why, when you have slope-intercept form, the y-intercept is this last value here, because if you plugged in 0 for x to try to find the y-intercept, well, that's all that's left, right? So that's why that works out. All right, cool. Hopefully we're all good on graphing linear functions. Again, largely an Algebra 1 review, but you probably did not do problems like that in Algebra 1. Still, it's just a little review of how to manipulate expressions algebraically, which is pretty nice. All right, let's start talking about characteristics. Okay? And then we'll go back to our do now and find the characteristics of those as well. I made a photocopy of this. I don't know if you can tell based on the quality, just so I wouldn't have to draw the graphs like 3 or 4 times. So I apologize if the image quality is bad, but I'm looking on the preview and it looks okay. So characteristics of functions. Again, characteristics of functions are pieces of information that you should be able to extract from a function just by looking at the graph. Okay? We've done 2 of them already. Characteristics of functions that we've done. We've done domain. Right? And just to refresh you on the definition, the domain is the space that the graph occupies with respect to the x-axis. That's how to find the domain visually. The domain is really the set of all possible input values, but visually we say, where does it occupy with respect to the x-axis? If I look to the left, if I look to the right, how far does the function go? The range asks the same question, but instead of looking left to right, we're looking bottom to top. It's the space that the graph occupies with respect to the y-axis. Okay? In other words, it's all possible output values of a particular function. We find it very similarly to the domain, where we scan bottom to top and we ask ourselves, how far down does this function go? Well, this arrow would mean it goes down forever, spoilers. And how far up does this function go? This one does not go up forever, so we would specify whatever that value is. All right? A couple other characteristics we can identify for sure. We can identify the X intercepts. That's a word that we've just used, but I will officially define it for you now. The x-intercept is, of course, a point, there could be more than one, at which a function crosses the x-axis. That's known as an x-intercept. We also have the y-intercept, obviously goes right along with that. And again, this is something we've already done. And it's the point, because there could only be one y-intercept, at which a function crosses the y-axis. The reason there can only be one y-intercept is because otherwise it wouldn't be a function. It would fail something called the vertical line test. You may remember that from Algebra 1. So that's why it can only have one y-intercept, but it could have multiple x-intercepts like you see here. Okay. One word that you haven't heard of though yet is the end behavior. Okay. And the way that I would find, you probably see it written down here. The way that I would define end behavior is, it is the expected direction or trajectory, if you want to use a fancy word. But I'll say, no, not directory. The expected direction. Direction. We can make that, we can fix that. The expected direction, I got the two words mixed up, of the function as x approaches negative infinity or positive infinity. Okay? It's the expected direction of the function as x approaches negative infinity or as x approaches positive infinity. The way that we write the end behavior is we always start with two lines of end behavior. And we say as x arrow negative infinity. What that means, the way I read that, is I'd say as x approaches negative infinity. I then say f of x, the function approaches, and then we fill that in with whatever it approaches. It's either going to be positive infinity or negative infinity. Okay? I also have my second part of end behavior here. So this part talks about the left. As x approaches negative infinity means as your x's get smaller and smaller and smaller, as we continue to the left, what does the function do? We also have as x approaches positive infinity. Means now the opposite. As we continue to trend to the right, what does the function do? We'd say f of x does something. And we have to fill in what that thing is. But typically, these two lines of end behavior are always the same. All right? There are a few exceptions. The one big exception is if a function has an endpoint, then you do not have to specify end behavior for that particular side. So I will put a little note here, and I'll say if a function has an endpoint, meaning not an arrow, then it is not necessary to identify end behavior for that particular side. And the reason is because end behavior is trying to describe what we see beyond the boundaries of the picture. So beyond the boundaries of the picture, what are we expecting this function to do? What is the behavior of this function as it approaches those extreme ends? That's why it's called end behavior. Okay? If a function stops, well then I don't need to talk about end behavior because clearly the function has already ended. Say this function, for example, stopped here where my pen is pointed at this point. Well, why would I talk about as x approaches positive infinity? It's never going to get even close to positive infinity because it's stopped already, right? There's no arrow where it's continuing on infinitely. If it ends, then it ends. We don't need to talk about end behavior on that particular side. If there are two endpoints, then we would actually indicate that there is no end behavior, okay? So I'll make one more note. I wish I kind of left myself a little bit more space here, but I'll make one more note and I'll say two endpoints implies that there is no end behavior. And we would actually write that as the response. If it asks for end behavior and you're dealing with a function that has two endpoints, you would respond and you would say there is no end behavior because the function has ended. Why are we going to talk about what happens as we approach infinity and negative infinity if it ended on both sides? And it's self-contained and that's it, right? There's no reason to even bring that up. All right, anyway, let's try to approach these questions now down here, and then we'll return to our linear function that we did at the beginning and see if we can tackle that as well. So let's start with something like this. If this is asking you what is f of -4, and this is the graph of f of x. Well, remember that f of -4, when we're solving an equation, that means we want to take -4, plug it in for x, and see what we get. And if you remember the point that I made previously, the value that we get would be the y coordinate that would match with this x coordinate, meaning that that would be a coordinate on the graph. That would be a point on the graph. Well, the same thing is true in reverse. If I'm trying to find f of -4, well, let's see. -4 would be my x value, and I'm trying to find out what y value pairs with that -4. I would look here, I would see -1, 2, 3, 4. Which y value pairs with that? It's going to be 1, 2, 3, 4, +4, right? Because there is a point at -4, 4, I'm able to say, oh, well, what y value gets spit out of the function when we plug in -4? What's the output for that? It's 4. Okay, so f of -4 would be 4. Again, we look at the x, we say, oh, it goes to -4. And at that value, it's 4. So f of -4 is 4. Okay, I see that on the SATs being asked a lot, and a lot of the practice materials and stuff. They always ask questions like this. Look at the graph. What is f of 6, for example, which is our next question, and it'll ask you. F of 6, again, means 6 is your x. So let's look at x coordinate 6, 3, 4, 5, 6 right there. What does our graph tell us that the y coordinate is that matches with 6? It's -1. And next, I would look for f of 0. F of 0 is a great question. We're trying to see, for x coordinate 0 is here. What coordinate matches up with that? It looks like it's at 3.5 or 3.5 or 7/2. So I can say it's at 3.5. Okay, or 3.5 or 7/2. Make sense? Hopefully. The next question is essentially asking the opposite. Instead of giving you the x value and asking you what y value matches with that, now I'm essentially giving you the y value. When does this function output 0, and asking you for what x values does that happen? Notice there could be more than one answer for when you get a particular number from a function. Great example of that is x squared. If you look at the function of f of x equals x squared, if you plug in 2, you get 4, right? 2 squared is 4. And if you plug in -2, you also get 4. That's okay. It's okay to have the same output resulting from two different inputs. That's fine. You just can't have the other way around. You can't have 2 go to one answer and then you plug in 2 again and it somehow goes to a different answer. That's bad news for a function, but this is fine. So there can be more than one, and in this graph we see if there is more than one. I would say, well, when does the graph output 0? That's going to happen if we input the x value of 4. And it will also happen if we input the x value of -5. And to indicate those answers properly, because we are using set notation, here we are listing elements for which the values of x will output 0. So I would use my curly brackets to list those things. All right, let's keep going from here. Domain, we already know how to do. How far to the left does it go? How far to the right does it go? It's -infinity to infinity, all real numbers. The range, how far down does it go? How far up does it go? We see that this function will go down forever, hence the 2 arrows. But it does not go up forever. It only goes up to 1, 2, 3, 4, 5, 6 at its highest. It does include 6 though, so we're going to use our square bracket. And lastly, the end behavior. Ready? I would say as x approaches -infinity, f of x, meaning as my function, as my x values get smaller, as we progress this way on the x-axis, are we expecting the graph to approach positive infinity? Are we expecting the function to go up to positive infinity? Or are we expecting the function to go down to negative infinity? And we would see clearly on the left side here, the function is going down. So I would say as x approaches negative infinity, so as we scan this way, the graph, the function, is going down, approaches negative infinity. Notice the same thing is true on the other side. For this particular example, I would say as x approaches positive infinity, as we continue to scan this way, notice the function is going down, right? F of x approaches negative infinity as well. Okay? If this were curving back up here, then we would say f of x approaches positive infinity because then it would be going up. But as we go to the right, the function is clearly decreasing forever. It is going to go down and down and down, negative infinity. All right? That was a little bit of a long-winded explanation, I know, for that particular example. But now that we did that, we should be able to speed through our second example here. F of negative 1, for looking at this parabola, f of negative 1 means if I plug in negative 1, what do I get? 4 in this particular case, because the point that the y-coordinate that matches up with that x-coordinate of negative 1 is positive 4. Next, f of negative 3. What y value matches up with negative 3? Here's negative 3 right here. Ooh, looks like it's 0, because it's sitting right on the x-axis. That's pretty nice. F of 0, again, we're looking here, 1, 2, 3, it would be 3. If you notice, f of 0 is another way to ask for the y-intercept, by the way. Do you notice that? Because if we're plugging in 0 for x, that's exactly what we just did, we're going to get the y-intercept. Kind of neat. Next, we're asking the same question for which values of x does f of x equal 0. Here, it's positive 1 and negative 3. So I'm going to use my curly bracket, negative 3 and 1. Notice that's the x values for which the y value is 0. Domain we already know how to do. How far to the left does it go? Negative infinity, because this extends forever to the left. This extends forever to the right, so that answers the question of how far to the right it goes. We get negative infinity to infinity. Range, how far down does it go? It does go to negative infinity. How far up does it go? It only goes up to 4. And for my end behavior, once more, I would say as x approaches negative infinity, meaning as we continue to the left forever, what are we expecting our function to do? Well, our function is decreasing. It's going down to the left. So I would say the function f of x approaches negative infinity. And on the other side, we say as x approaches positive infinity, that means as our x-coordinates continue to get larger, what is our function doing? It is, just like the previous one, going down again. Alrighty. So that's how we can fill in some points specifically, if I ask you specific points, as well as the x and y intercepts. You should be able to look at any graph and identify those quickly. And here's some sneaky ways to ask for y-intercept and x-intercepts, and the end behavior. Let's quickly return to our graph that we started class with right here. And we should be able to identify those pieces of information, right? We should be able to identify the x-intercept. We did that already. That was right here, 10, 0. We should be able to identify the y-intercept. We did that already, 0, 5. You could also look at the graph, of course, or you could look at the slope-intercept form, and it tells you. We can ask for the domain. Since it's a linear function and it's a sloped line, you already know the domain of that. It's going to be all real numbers, which is supported by the fact that it extends forever in both directions. The range, this also extends forever bottom to top. It's all real numbers. Goes down forever, goes up forever. And lastly, I can ask for the end behavior. And we would say as x approaches negative infinity, means as we go to the left forever and ever and ever and ever, which way does the function go? Does it go down to negative infinity, or does it go up to positive infinity? And you can see by the arrow pointing up here on the left side, I would say, oh, well, my function f of x approaches positive infinity, right? This side, though, is still going to be negative infinity, because you can see as x approaches positive infinity, that means as your x-coordinates continue to increase, meaning you're just moving this way, what are we expecting from our y-coordinates? Well, our y-coordinates are continuing to decrease as my x's increase, right? Because they're just going to keep getting lower and lower and lower. So I would say my y-coordinates, f of x, the function, decreases, approaches negative infinity. And I think that does it. Hopefully no questions on that, but if you do have a question, please do not hesitate to reach out and ask. There are some practice problems posted alongside this video that I would like you to try on your own. They're linked on Google Classroom. Just a quick little recap. We did a little example of graphing a line. I then talked to you about domain, range, x-intercept, y-intercept, and end behavior. You probably already knew the first 4, but I don't think you've seen end behavior before. We looked at a couple examples where we can evaluate specific points on a graph, as well as identify these characteristics. Same thing with this example here. And then we brought it back to the one we started with and went through that as well. All right. If you do have any questions, like I said, please reach out. But thank you for your attention and focus today. I hope you have a great rest of your day, and hopefully you learned something. So I will see you next time. Take care.